So now that we've talked about conduction, our next thing to talk about is going to be convection. Convection is energy transfer between a solid surface and the adjacent gas or liquid. Okay, and convection has two components. You're going to have a lot of things. I'm going to say a lot of things about convection that has two components. Okay, the first one is conduction. Okay, you're going to have conduction. You're going to have that energy diffusion between something and something else. So it's going to be here, it's between a solid surface and a liquid, or solid surface and a gas. You're going to be diffusing energy. As long as there's a temperature gradient, that's going to occur. Okay, so I'm going to write here diffusion of energy. And the other one is advection. Advection is the bulk movement of energy away from a surface. So it's flowing away. So that's the difference. Oh, we have a visitor of a cat. See, there's a cat here. This is Fiona behind me. There we go. What's happening is you are diffusing energy into that liquid or gas, and then that liquid or gas is moving that energy away. Convection. That's where we get the word. All right, if it was sitting there, even if it was sitting there, so you might say, well, what if it happens if I don't have any blowing or moving away? Well, what's often going to happen if you add energy to a surface, to a liquid or a gas, you're going to change the density of that liquid or gas, and it's going to move away. Again, it's going to naturally take that energy away. So multiple ways this can be done. In fact, two ways this can be done, and that is going to be, we have here two types. We're going to have free convection. Free convection, which we're going to have buoyancy forces that dominate. Okay, so that's what's happening right now. I've often talked about my head is giving off heat to the air around it. So what's going to happen here is that's going to be heating up the air around it, changing the density, and that density is going to is going to cause that buoyancy effect to happen and that air to move away. Okay, that's free convection. And if you want to look up some very interesting videos, there's something called Schlieren photography, S-C-H-L-I-E-R-E-N photography, where they can actually look at the density changes of air and see it. And so it's very interesting. It's a very there's a lot of YouTube videos out there about Schlieren photography. The other one is forced convection. Forced convection is going to have an external mechanism. So you're going to have a fan or a pump, pumping the water or blowing. Oh, look, we have a second cat here. This is Finn in the background. Okay, so typically we'll have one of these two types are going to dominate. You're always going to have some bit free in forced convection, and you might have a little bit of forced convection in free convection, but it's which one is the dominant effect that you have there is what we talk about. And so this is going to be the law we're going to be talking about is Newton's law of cooling. Okay, Newton's law of cooling, again, we're going to provide it to you. Q dot convection is equal to, and I'm just going to write these things down here, HA, the surface area, times TB minus TF. Okay, what does this mean? Well, of course, this is going to be the rate of convective heat transfer. Okay, rate of convective heat transfer. Now H is going to be the heat transfer coefficient. And this is going to have units of watts per meter squared Kelvin, or BTUs per hour per inch squared degree Rankine. Okay. Now the heat transfer coefficient is not a property. First we talked about the thermal conductivity is a property. The heat transfer coefficient is not a property. In fact, when you take heat transfer, you will spend a month trying to find the heat transfer coefficients for different objects. For example, the heat transfer coefficient will change of a surface if you have laminar flow, nice smooth flow going over something, or turbulent flow, mixing flow going across. If you have smooth surfaces and rough surfaces, all of these things, the temperatures of the airs, all that changes can help us change the heat transfer coefficient. It is a complicated matter. It's not just something they say, oh, it's aluminum. It has this heat transfer coefficient. Oh, is the aluminum smooth? Is there turbulent air going over the aluminum? We have to know all of that information. Okay, so, and even when we do that, we do a lot of experimental work to find heat transfer coefficients. We do a lot of computational work to find heat transfer coefficients. And sometimes we're not very close to what we compute, or an equation or a relationship that we get for heat transfer coefficient is not close to, or I shouldn't say not close, it's within 15%, 15 to 20% of the real exact heat transfer coefficient. So we don't have really good models yet to be able to calculate these things with an equation. But when we get within 15%, if our calculations within 15%, man, we go overboard. We're like excited. Hey, we got something. This equation really works. And we celebrate it. But can you imagine if at the very end of the semester, if I said, I'm within 15% of your final grade, you got an 85 or you got a 60. That's a complete different thing. That you would think that wouldn't be a good thing, but in heat transfer coefficients, we're overjoyed about that. All right. AS is going to be the surface area as well. Okay, and TB and TF. What I'm going to call this TB is, I could do this T2 and T1. It really doesn't matter what I do here. I'm going to say TB is the temperature of the base or the surface, and TF is going to be the temperature of the fluid. Now, your book sometimes calls this TS minus temperature of the surface minus temperature of the surroundings. Well, that's why I like to use B and F, because surface, S-U-R-F, surroundings, S-U-R-R. There's lots of things there, just kind of like conduction, convection. So I try to give you a little different lettering system, TB and TF. Now the things you need to know about these here, the thing you know about this equation is you're going to have the highest temperature first. Okay, if your liquid is hotter, then it goes first. If your surface is hotter, it goes first. It doesn't matter which one it is, it goes first. You can change the order of these and it just doesn't matter. We just need to figure out what delta T is. What you again have to determine when you're not plugging and chugging here is you're going to have to determine which direction the heat transfer is going. Is it going into the liquid or is it coming from the liquid? And that's going to be important for you when you're trying to calculate the sign convection of the heat, the sign convention of the heat transfer when you're looking at your system. So that is going to be very, very important there. So again, you put the highest temperature first, and then you have to know, okay, is it coming out of my surface or coming into my surface? And that's going to help you with the sign convention when you deal with your system. Remember, coming into a system is positive, leaving a system is negative. All right, here. Now, we have a range of typical heat transfer coefficients. So the range of typical heat transfer coefficients. So let's talk about free convection. Free convection. In gases, you're going to have, if your H value in, we'll put it in watts per meter squared Kelvin, gases you're going to go between 2 and 25, and for liquids, you're going to have between 50 and 1,000. So of course you're going to have much better heat transfer with liquids than you are with gases. Okay, if we have forced convection, and we're talking about gases and liquids, we can go between 25 and 250 and between 50 and 20,000. Okay, so when we're talking about heat transfer, we're talking about convection, there's a lot of things we can do to have better heat transfer, and I'm going to bring some of these things into our in-class portion of this. You know, we're talking about radiators and heat sinks and fins. We put a lot of fins on things. Why do we put fins on things that we want to have convective heat transfer? Well, fins add more surface area. The more surface area, if you look up this equation, the more surface area, the bigger the rate of heat convective heat transfer is going to be. We can change the surface properties because we can change the heat transfer coefficient. Also, we would like to have a liquid go over something rather than a gas go over something, because liquid's going to have higher heat transfer and going to have more of that coming out. So you see this all the time. If you're wanting to, tonight I was wanting to make we made some enchiladas. Where my family's a bunch of meat eaters, and so I have from home. My parents got me some ground beef, and I had it frozen, and I wanted to thaw that. And I thought, how am I going to thaw this fast? I threw it into some water, because the water is going to there'll be more heat transfer with that water, and we're going to have I'm going to thaw the hamburger faster than if I just let it out on the counter in the air for it to thaw. So these are things you deal with in an everyday situations, but now we just put some numbers to them. So this is convection. All right, next thing we'll go to is going to be radiation.